So
You haven't learned it yet.
58 says, determine whether the following point lies on the given line. Please stop talking. So we have this point and this. Oh, thank you. Okay, so we have this, right? So one thing that you can do is I'm going to kind of resort this into a form that makes it a little bit easier to deal with. So I'm going to have basically like so I have negative ti minus 8j plus 4tj. Guess those are vectors. So if I rearrange this, I have minus 5i plus 4j times t. And then we'll have plus like negative 8j. And I'll write, actually I'm going to write 0i minus 8j there. Is that okay? So we can kind of translate this then into our more familiar form like this. And all we really need to do then is solve this system to determine if it holds for the value t. Now, pretty clearly, looking at the first equation, I can see t has to be negative 3, just dividing both sides by negative 5. If I plug negative 3 in for t here, I get negative 12 minus 8, which is negative 20. So it seems like everything holds. So I would conclude that that point does lie on that line. Probably the trickiest thing was like taking that linear combination form and sorting it back out into that more familiar form. But it really could have still been accomplished here at the beginning, since this is really like 15i minus 20j. So you could have like substituted that in and kind of done the same thing. And it should have worked as well, the same value of t. Or you would have gotten the same value of t, but I assume that we're not very comfortable with the linear combination form, so I wanted to do the transformation to the situation you probably feel better about, especially given that you didn't ask questions about like 55 or 56, which was in the more familiar form. So I assume that would be okay if I did that. Keys. Yeah, it's like almost the identical problem. It's a little bit easier because we don't have to do that transformation part. So basically all I need to do is solve this system. Are you okay with how I made that system? Okay, so again, for everybody else, that's the x has to equal the x, and the y has to give me the y's. So if I solve for t then, Add the 3 over, I get 8. Divide by the -2, I should get -4. If I plug -4 back in here, I get -12 plus 14, which is 2. So, oops, I didn't mean x, I meant t. So that looks like it works, right? You're just making sure that when we solve for t, you're getting the same t in both equations. So is there a unique value of t that I can plug in to generate that point? If the answer is yes, then that point lies on the line. If the answer is no, it doesn't. That's basically the whole idea there. Same idea as if you wanted to test if a point lies on a line, just a regular equation for a line, right? You just plug in, you plug the x in and see if you get the right y back out. That's basically all we're doing. Yeah, no problem, man. Cass? Sure. So 69 says, find a possible vector line equation in IB component form for a line that intersects the following points. So just FYI, there's like 4 possible answers. I'm not going to do all of them. I'm just going to explain to you one of them and then talk about the others. So in order to write the equation for the line, what I need is a point and a slope. So let's pick one of these. I'm just going to pick the first one. And then I'm going to make the slope. So let's do 5 minus 4 over -2 minus 3. So I have -1/5 for my slope. So that slope is going to give me the direction vector 5, 1, and it doesn't matter which number I attach the negative to, although it constitutes like a different version of the same answer, but it doesn't matter if I attach it to the 5 or the 1. And my point vector then is going to be -5, 2. So my R is, or one possible R would be that. Is that okay? And again, you could have picked this as your R0. You could have used the other point, and you could have put the negative sign in the other place. So that's like the 4 combinations of answers you could get, depending on which point you picked and where you put that negative sign. If that was a positive 1/5, the other answer you could have is both the components are negative, right? Okay. Cool. Anybody else with questions? I'm happy to do a little bit more if we need to before we get going. Sophia. 68 says, find the slope-intercept form for the following lines given as vectors. So we're just going backwards to the slope-intercept equation. Okay. So basically what I'm going to do is kind of that same transformation that I did in 58 that we started with. So I'm going to kind of distribute the i's and j's through. So far, so good there. Okay, and then I'm going to just group the things together. So the stuff without the t's is going to go in one group, and the stuff with the t's is going to go in the other group. And that's going to allow me to just write that in our IB component form. And then from there, it's pretty easy. There's a point, and there's a slope. So I can say y equals negative 3 over 2x minus 1/2. Does that feel okay, Sophia? Yeah, and again, like, you can go straight to the point and the slope from the IB component, or from the, not the IB, the unit vector representation. I forget what that's called. But I think it's, for most of us, it's usually easier to convert it into this like column vector form to pull the point and the slope out of. You don't need to do it that way, but I feel like that's a skill that's useful to have, and it's a pretty easy thing to do. Keep 60. Sure. So this says find a possible vector line equation in the linear combination form. That's the form that we're into. That's the ones with the i's and the j's in it. It's the linear combination form. For the following lines given in slope-intercept form. So y equals negative 6x plus 4. So the first thing I'm going to do is I'm just going to write this in IB component form. So my point is I'm just going to use the slope, or the y-intercept. And the slope I'm going to use just reading from the equation. Good with that? Okay. So the point vector, or that point becomes my point vector. And the slope becomes my direction vector. And it doesn't matter where I put the negative sign, whether it's on the 1 or the 6. Either place is fine, but not both. So that's going to give me this vector equation. But that's in the wrong form. That's in IB component form rather than the linear combination form. So to turn it into the linear combination form, all I do is I tack on the I to the X component and the J onto the Y component and turn it into an addition problem. And then usually we group the I's together. So obviously I don't need the 0 I really there, but I put it there just for it to be easier for you guys to follow the work or whatever. So usually we write it that way, with the I's kind of grouped together and the J's kind of grouped together. Does that make sense? So a lot of it's just like remembering the names of these things and the vocab. And I know it's kind of a lot of vocab in this chapter, and it's a pretty beefy chapter. So there's a lot of like these different forms and different names and like going back and forth between these different forms and these different representations and all that. Cass?
I have a question about this problem. If you put the I's and the J's out, so they're on the outside of the equation.
Oh, yeah. So Cass is saying that, could I write it like this? Absolutely, that would be fine also. And probably that would be the more standard way of it being written. That's probably what the answer key has it look like, right? You don't need it check yet. But yeah, that would be definitely okay too. In fact, probably better, because it's less symbols. And that's what we strive for as mathematicians, right? What minimum number of symbols written. Keaton, did you have a hand up also?
I was just going to ask if we're having one test for all these.
So my plan, at least at this point, is I think that basically I have 2 more days I think that I'll need to finish out this chapter. So today and the next lesson. So that would be Monday. We'll take a day next week to kind of settle things on Wednesday or whatever. And then I think you have scheduled asynchronous learning days on Friday and then Monday. My plan was to do the test on the asynchronous day and let you just kind of do it at home. So that allows me maybe a little bit more flexibility to just make one test that maybe runs a little bit long, since we don't have class periods per se on that day. But that's kind of where my head's at. We can talk more about it next week. But that feels like gives enough flexibility that if something happens weather-wise and it needs to get bumped, we still have time before the break hits to bump it and figure it out. So, okay. Yeah, no problem. And I put that on the calendar already, if you noticed on PowerSchool. I did that also. Not that it can't change, but I figured it's better to get something, right? All right. What do you guys think? Are we ready to rock and roll? All right. Let's do this. Okay. So this first section we're going to look at is about just the 3D coordinate system. So up until this point, we've been talking about everything 2D, right? 2D vectors, 2D points, 2D lines, all that jazz. We're going to now start moving into 3-dimensional pieces. So the first thing we want to talk about are the 3-dimensional axes. So you can't draw a 3-dimensional axis on a sheet of paper without using a little bit of imagination to think about the perspective. So what I'd like you to do is kind of look at some corner of the room and look at the bottom part of the room. So you have the corners of the floor that meet, and then you have the edge that's going up the wall, right? Everybody kind of see that? Okay. So usually when we draw a 3-dimensional axis, we're going to basically draw that picture, but we're going to draw both ends of those axes. So this axis is basically there. This piece is like this piece, and then this piece is like this piece. Everybody okay with that idea? One of the things that drive students crazy about is the way we've named these. So that axis that's coming out of the paper towards you is we call the x-axis. The side that's kind of in the parallel to the paper is the y-axis, and the one going up and down is called the z-axis. So it's basically like you took your xy plane and you turned it flat and then stuck a new axis on it, is basically what we're trying to represent there. This is the positive end of the y, so that's the negative end. This is the positive end of the x, so that's the negative end of the x. That's the positive end of the z, so that's the negative end of the z. Is everybody okay with that orientation? It's new, it's a little different, but all right, if you tell me that's the way it is, that's the way it is. That sucks or whatever, but I'd rather have the x and y in the same position that they normally are, with the z being the new one that we've added in there, but this is the convention, so just going to have to deal with it. All right, so let's practice what it takes to graph a point. So let's say we want to graph the point 325. Again, the order in which we write our coordinates is going to be always alphabetical. That's the convention. So x is first, and then y, then z. So let's do that. I'm going to use my OneNote to put in my 3D axis. So I'm going to take here's my x, my y, and my z. And I'm going to start by drawing in 3 tick marks on the positive x-axis, 2 tick marks on the positive y-axis, and then 5 tick marks on the positive z-axis. Okay with that? So like 1, 2, 3, 1, 2, 1, 2, 3, 4, 5. Okay. And now basically what I'm going to do is I'm going to start by drawing a square on the xy plane. So I'm going to start on the positive x-axis, and I'm going to draw a line that's parallel to the y-axis. And then I'm going to go to the y-axis, to positive 2 on the y-axis, and draw a line that's parallel to the x-axis. I'm going to note where they intersect. And basically observe that I have this, this is really a square, but because it's drawn with perspective, it doesn't look like a square. How many of you have taken the art class where you do perspective drawing? Some of us have. Nobody? Would be helpful in this case. It helps with the imagination if you're used to things being square but not looking square when you draw them with perspective. Anyway, so we have this part. What I'm going to do then is I'm going to project this upward. So each one of these 4 corners I'm going to draw up. So here I'm drawing up to z equals 5. Here is in the same plane, so it's going to go up the same height. But here, it's not going to go up as high, right? I'm going to just kind of eyeball and try to make that line the same length as these other 2 lines that I drew, but I'm just kind of eyeballing it. But if you look at what I did, it's probably pretty close, right? And I'm going to do the same thing here. I'm going to go ahead and draw my line about the same height. And I basically have made this rectangular prism here, this box. Everybody okay with what I've drawn here? So where is the point that I've actually graphed? Well, let's see. We start at the origin, and we go 5 in the x direction. Then we go 2 in the y direction. And then we go 5 in the z direction. So that is the location of the point 3, 2, 5. I just needed to draw the rest of that box so I was able to kind of get everything in the right proportions. If that makes any sense to you guys. We can do another one here in a moment. And while that feels like, boy, that's a heck of a lot more complicated than 2D, you're right, it is. But it's also one of those things like, if you practice it a little bit, it's really not so bad. Again, if you have a background with some perspective drawing, if you had done that in art class, that helps a little bit here because you're used to scaling things the same way when you're drawing in perspective. I'm really surprised that nobody raised their hand in having done that. I thought that was like Art Foundations class you would do that. Maybe you guys haven't taken it. I don't know.
That little project thing that skipped over.
Oh, it would have been something you did during quarantine. Got it. What a bummer. Okay. Well, what do you guys think? Is that okay? Do we need to do that again? You tell me. Again, I know how to do this. I'm not doing it for my benefit. I'm doing it for yours. If you tell me you're good, I'll keep going. If you tell me you want to see another, we can do another. Okay. No response. I'll assume you got it. If you change your mind, we'll always have questions later, so we can always ask about it again. No big deal. Couple of quick definitions. So your 3D distance formula. So in 2D, this is the square root of the difference in x's squared plus the difference in y squared. In 3D, you basically have the analog. So you exactly what you'd hope, just with the appropriate modification. So we just add a third component to it. So it looks just, oh my goodness, that's not a plus sign there. So it looks just like the distance formula in 2 dimensions with that third component added in there. Not surprising, that's pretty much what we'd hope for and expect. Midpoint, same way. So remember, in 2 dimensions, the midpoint is like the average of the x coordinates and the average of the y coordinates. So in 3D, it's the same thing. The average of the x's, the average of the y's, and also the average of the So no big deal, just a couple of formulas there. So let's say we want to find the distance and the midpoint for these 2 points. So the distance formula, it doesn't matter which one I call 0.1 or 0.2. I'm going to call the first one 0.1, the second one 0.2. So doing the distance formula. And when I type all those little quantities in my calculator and add them up, I get 534, which is about 21.1, depending on if the answer is asking to round or leave it exact. I don't know, tomato, tomato. And the midpoint then is 6 plus negative 8 divided by 2, negative 8 plus 5 by 2, or negative 1, negative 3 over 2. You can make those decimals too if you want, but I like fractions, so I'll just leave them as fraction. So far, so good? That's it for that section. So you graphed them, found midpoints and distances, and like, that's it. Next section. So in section 8.6, we're going to talk about 3D vectors. So let's just do, I'm just going to make like a little chart here. So we're just going to put like the form or the name or the definition or whatever, and I'm just going to write in the 2D and then the 3D one just so we can, it helps review the 2D stuff and then you can compare it to the 3D. Is that okay? So the first one is just component form, and then we have IB component form. So for head minus tail, we had like x2 minus x1, y2 minus y1. So the same idea for 3Ds, but we have an extra component. So the magnitude there, same idea. So okay. Notice that I'm going to skip the direction of a vector, like the angle representation for the direction of vector. Does that make sense in 3 dimensions? No, right? So like when we talk about the direction of a vector in more than 2 dimensions, the angle goes out the window. You're just going to describe it with a vector. So the component description, or the unit vector description of direction, is going to be what we would use in a 3-dimensional setting, but I'm just going to kind of skip the angle representation there because it doesn't really matter. So our standard unit vectors in 2 dimensions are these guys, the I and the J. In 3 dimensions, we have a third unit vector, K. Okay, come on here. And then the linear combination form is obviously, you know, the same analog that we've been doing. Right, no big deal there. The sum of 2 vectors so for adding vectors u and v in 2 dimensions, we add 2 components. In 3-dimension, we components. Whoa! The vector additive inverse, so negative u, just negative u1 dimensions. In 3 dimensions, it's the same thing. The scalar product. Oops. Again, we just multiply k to each component. So everything is working pretty much exactly the same, right? Dot products. and that all the dot product properties obviously still hold in 3 dimensions. There's nothing dimensional specific about those. So I just kind of ripped through all of that, but it's basically everything works exactly the same way. You just have a third component, right? That's the takeaway. So nothing complicated about that. We'll do some examples here in a moment, but I can tell that everybody's still scrabbling hurriedly, so I'll pause here and let everybody kind of catch up a little bit. Sophia. K. Yep. Just I, J, K, like alphabetical order. So we try to do things that make sense as much as we can in math when we name them. Absolutely. So we'll do a little example here. Practice kind of doing this stuff again. So we're going to find and graph the vector w, which is equal to 2 times the vector u plus the vector v, where u and v are the given vectors. I'm going to go ahead and start by just transforming vector v into its component form definition. So rather than writing as a linear combination, I'm going to write it as a component form. You could have done the reverse and written u as the component, or the linear combination form from component form, but I don't know why you'd want to do that, as it's more symbols to write. But you could have. So what do we get? We get 4. I'm sorry. Yeah. 3, 2, 5. It's a mess 6. I almost thought it was a 4. It's a shame when you can't even read your own penmanship, right? Ever happened to you? Yeah. Okay. So then we are also asked to graph that vector. Yes, Ava? Of course. So how are we going to graph this vector? Well, I don't want to do that. The same way that we would have graphed the vector in the 2-dimensional. Well, we graphed a point, but that is this is a vector, but it's very similar. So that's worth pointing out. So when you guys graphed a point, you just put the dot, right? Wherever it went. You went 1 over and 2 up and drew a dot. When you vector 1, 2 in 2 dimensions, you put a dot at 1, 2, and then you drew a line from the origin to 1, 2, right? How are we going to draw a vector in 3 dimensions? We're going to plot the point, and then we're going to draw the arrow from the origin to there. Here's our x, y, z axis. I'm going to put 3 tick marks on the x, 2 tick marks on the y, and 5 tick marks on. And as Ava's pointed out already, this is the same point that we graphed earlier. But I'm going to still kind of start the same way. So there's my line. So there's that. So there's my point. There's the origin. So there's my vector W. Okay with that? Okay. Guess what? That's the end of that section. Now we have one more. There are 8 sections in this chapter. We're doing 3 of them today. Well, those first 2 were kind of like not a lot I mean a lot happened, but like nothing really new happened. We just modified things that we had done to do 3 dimensions. Like probably the hardest thing in there was graphing the points, or the least familiar anyways. Okay. So 3D vector equations for a line. This is where these vector line equations become quite useful to us, because there isn't a good linear way to write an equation for a line in 3 dimensions, because if you write an equation with x, y, and z in it, what you're describing is a plane. So having an equation for a line in 3-dimensional space really kind of requires you to use a vector component. Now, when we wrote the equation for a line in 2-dimensional space, we needed a slope and a point, right? What does slope mean in 3 dimensions? Doesn't really have a representation, right? Because there's not like rise over run, because there's 3 components. So what are we going to need to really get away from is thinking about slopes. And really we have to start thinking about a direction vector. Remember this, that direction vector basically is going to describe the tilt of our line in 2 dimensions. In 3 dimensions, it's going to kind of describe still the tilt, but also like the orientation, because we have like 3 dimensions of space to kind of do that in. But a vector will be a good representation of that. So let's go ahead and do an example. So let's say we want to write the vector equation for a line that passes through these 2 points. Everybody okay with that? So what we're going to do is I'm going to create a component form vector that goes through those 2 points. So I want a vector that's going to basically be in the same direction of those 2 points. I can do that by just finding the component form vector that goes through those 2 points. That's going to be my direction vector. It doesn't matter if I go from which one is the head and which one is the tail. It'll be fine. And then I need that direction vector to be starting at one of those 2 points. So one of those 2 points will represent my P0 or my vector R0. Doesn't matter which one I choose. So again, there's going to be like 4 representations for this equation for a line, depending on which one you pick as the head or the tail, and then which point you pick to put into your equation. But we're still doing the same equation for our line. So we're still doing r is equal to r naught plus vector v times t. So for our vector v, we'll just find the component form using those 2 points. Doesn't matter which one we call the head and which one we call the tail, so it doesn't matter which one goes first and which one goes second. Everybody's okay with what I did there? So that's going to give me 8, -6, 5. And then for my R0, it doesn't matter which one of those I pick as my R0. I'm just going to, for the sake of argument, pick the first one. And then typically we write these in component form, or I'm sorry, IB component form. So that's it. No big deal, right? Yes, sir.
If we are not, it's just like rewriting the numbers.
So I'm just using either of the 2 points and just turning that into a vector.
Okay.
So think about what it is that we're doing. Again, I'm going to think about this as a 2-dimensional one just because it's easier for me to draw the picture. But you're saying, okay, I have like, you know, some 2 points, right? And we want to draw a line through them. What I'm doing is I'm saying, okay, actually, let me put the points in a little bit different location. So let's say I have like this. So what I've done is I said, okay, I want this vector, right? Is basically what I'm going to try to get. So I create the component form for that vector, which is something that's going to be parallel. It's going to be in the same direction, but it starts at the origin. So what I need then is I need to add to it that component form vector, which is like just one of the points. So that's basically what we're doing. Does that help visualize what the equation is kind of saying? So if we add the green vector and the blue vector, we get the red vector, which is the vector in the same position as the line that we drew there. Cool? Okay. Again, I'll try my best to give you a visual representation of what we're doing whenever possible. And I'll try to do it as like a 2-dimensional analog because I think it's just easier to visualize what's going on because we're just more comfortable. So let's determine if that point, -5, 6, 11, lies on that vector equation for a line. How am I going to do this? The exact same way we would have done it for 2 dimensions. So I'm going to just create a system of 3 equations. Solve for the t. And see if that same t satisfies all 3 equations. Okay with how I created the system here? Okay. So that's okay. So that's my x. So there's my -5, and there's the rest of my system. And then there's my y, and there's the rest of that system. And there's my z, and there's the rest of that system.
Oh, that's okay.
Feel good?
Yeah.
Okay. Again, like,
I didn't know that the R was given.
yeah, it's subtle, and if you miss it, like,
Yeah.
but once you see it, it's like, okay, sure, that's how you make the system. Cool. That's beautiful because I can basically look at it and I don't have to do anything. All right, now I'm going to solve for t. Since there's only one variable in each one of these equations, I can just need one equation to solve for t. So if I add 3 to both sides, I get t is equal to -2. Okay, and then I'm just going to check to make sure that value of t holds in the other two equations. So if I go to the blue equation, if I plug negative 2 in for t, 12 minus 6 is 6. That one works. If I go to the second equation, I plug negative 2 in for t. 7 minus 2 times negative 2 is 7 plus 4, which is 11. So we're good. Everybody feel okay there? Okay. That's where we're going to stop it.